Okay, let's jump right into this explainer. Today, we're demystifying the top layers of the TCP/IP networking model and uncovering the invisible mechanics of the internet. You know, we interact with networks every single day, but we rarely get to peek under the hood to see the actual software mechanisms pulling all the strings. It feels completely instantaneous, doesn't it? You type a URL, hit enter, and boom, the web page is just there. But what actually happens in that split second? Answering this question takes us on a pretty fascinating journey straight down the network stack. It's this complex symphony of protocols, handshakes, and data packaging that all happens literally in the blink of an eye. To understand how your computer pulls this off, here's our agenda. We are going to meet the TCP/IP model, explore the application layer, move to the transport layer, compare TCP and UDP, talk about directing traffic with port numbers, and finally, track the entire encapsulation journey. First up, let's meet the TCP/IP model and get a look at the big picture. What's really brilliant about this framework is how it takes the massive, overwhelming complexity of networking and breaks it down into manageable categories called layers. Our focus today is strictly on those top two, application and transport. By isolating functions like this, a developer building a web browser doesn't have to stress out about the actual physics of a fiber optic cable. The top layers handle the software side, while the bottom layers completely take over for physical delivery. To make this a bit more concrete, think of the top layers as the people actually writing the letters and choosing the shipping method. The bottom layers, they act as the postal service, doing the actual physical delivery. Whether you're sending a letter across the street or all the way across the globe, the way you write that letter and stuff it in an envelope remains exactly the same. The postal network figures out the rest of the heavy lifting. Let's meet our letter writer. Section 2, the application layer. Now, a common misconception is that the application layer actually holds programs like Microsoft Word or Google Chrome. It doesn't. Rather, it acts as the absolutely crucial interface between your software and the network stack, using protocols like HTTP and DNS. It's essentially the gateway. When your web browser suddenly realizes it needs a resource from the internet, it talks directly to the application layer to kick off that process. Let's bring this to life for a second. Imagine a guy named Bob wanting a web page from his friend Larry. Bob's browser uses the HTTP protocol to specifically request a file, say an HTTP GET request for a file named home.htm, and Larry's server uses HTTP to send it right back. The application layer ensures that both Bob's browser and Larry's server are speaking the exact same language. But how does that message actually get prepped for travel? Once that letter is written, we move right to the mailroom. Section 3, the transport layer. Down here, the transport layer takes that application data and provides end-to-end transport services. And it does this using two main protocols, TCP and UDP. Below this layer, the IP network acts like a single unified highway. But up here at the transport layer, we suddenly have to make a choice between two very different delivery vehicles. So what's the goal here? The crucial point is that this layer prepares the application's data for the journey by segmenting it and deciding if it needs a guaranteed, completely reliable delivery. It literally takes a massive web page, breaks it down into bite-sized segments, numbers them, and ensures they arrive in the perfect order. Plus, it uses flow control to prevent a super fast sender from completely overwhelming a slower receiver. Section 4, TCP versus UDP. Let's compare those two primary shipping methods. Think of TCP like certified mail with return receipts. It's highly reliable, but it definitely takes more effort and overhead. UDP, on the other hand, is standard mail. It's blazing fast, making it perfect for real-time data like voice or video. Honestly, I'd tell you a UDP joke right now, but, well, I can't guarantee you'd actually get it, right? Okay, bad jokes aside, if you're downloading a crucial spreadsheet, you absolutely want TCP. If you drop even a single segment, the whole file is corrupted. But if you're on a VoIP call and you drop a tiny fraction of a second of audio, you probably won't even notice. UDP totally saves on overhead for those kinds of real-time apps. Now, to completely guarantee that delivery, TCP has to set up a connection-oriented session first. It does this through what's called a three-way handshake, and this happens before any real data is even sent. The sender essentially reaches out and says, "Hello, I'd like to sync up," using a SYN packet. The receiver replies, "I acknowledge your sync, and here's my sync back," with a SYN/AK. Finally, the sender acknowledges that, and a virtual circuit is formed. Only then does the actual data start flowing. And what if something goes wrong, if data gets lost in transit? TCP's sequence and acknowledgement numbers brilliantly step in to fix it. Imagine a sender transmits segments 1, 2, and 3. But segment 5 just mysteriously vanishes in transit. Because the receiver never officially acknowledges getting number 5, the sender instantly knows to fire it off again. That right there is the absolute magic of TCP reliability. Section 5. Directing traffic with port numbers. So if you have 5 browser tabs and an email client open all at once, how does the incoming data find the exact right window? It's all thanks to a process called multiplexing. The transport layer uses port numbers to keep everything organized. Think of an IP address like the street address of a large apartment building. It gets the data to the correct computer. But the destination port number, that acts like the specific apartment number. It ensures that Bob's HTTP web page data slides right under the door of his web browser and doesn't accidentally get shoved into his email app. A great way to think of these well-known port numbers is like standard customer service phone extensions. A web server, for instance, almost always listens on TCP port 80. An email server routing mail, that's going to be listening on TCP 25. Standardizing these ports across the board means your computer always knows exactly which door to knock on when requesting a specific service. And finally, Section 6, the encapsulation journey. Let's see how all this data gets packaged up to finally hit the physical network. It's incredible to watch how this builds. As data travels down the stack, it undergoes this process called encapsulation. It gets wrapped in specific protocol headers at every single step. It is literally just like placing a letter in an envelope, putting that envelope into a box, and then packing that box into a massive shipping crate. Each layer adds its own critical tracking information without ever peeking at the actual contents hidden inside the payload. Step by step, that original application data just keeps growing. First, it gains a TCP header, officially becoming a segment. Then it gets an IP header, becoming a packet. Finally, it gets wrapped into an LLC frame. Notice how the original block of data stays completely intact deep inside there. It just keeps getting thicker and thicker with headers until it's ultimately translated into the raw ones and zeros that travel across the physical wire. And honestly, the true genius of this modularity is that each layer only reads its own specific header. The transport layer only cares about the ports. It completely ignores the IP addresses being used by the network layer down below it. And when all that data finally arrives at its destination, the entire process just runs in reverse. The receiving computer decapsulates it layer by layer, peeling it back until the application gets that pure, original data. So, we've successfully prepared our data for shipping. We've written the letter, we encapsulated our application layer data inside a TCP segment with the correct port numbers, and it's officially ready to go. But that leaves us with a pretty thrilling question for our next explainer. Once that letter is handed over to the Postal Service, how do the lower layers actually route this packet across the globe, bouncing through dozens of completely unknown networks just to reach its exact destination? Really think about that the next time you hit enter in your browser.